Hey guys, welcome to another dynamics video. Today we're going to be doing a centripetal dynamics question about a car that's driving on a hill. And this question has two parts. Part A asks us, what is the minimum speed of the car if it were to lose contact with the top of the hill? And Part B asks us, what normal force acts on the car if it were to be moving at 10 meters per second at the bottom of the hill? The car weighs 2,000 kilograms and the radius of the hill is 50 meters. And feel free to pause the video and try to solve these questions for yourself. Okay, so let's dive into Part A. And Part A asks about the minimum speed for the car to lose contact with the hill. So what does it mean that it's going to lose contact with the hill? It means that as it drives over the top here, it's not going to be stuck to the ground, it's going to be in the air. So it's going to go with some velocity and it's going to go over the hill, like a car jumping over a ramp. So the minimum speed tells us that the car isn't going to be flying into the air. It's going to go with such velocity that it just barely grazes over the top of the hill, like a millimeter above the hill. So what does that tell us? Well, the first thing that it tells us is that the radius of the car's motion is going to basically be 50 meters because it's going to graze just above the top of the hill. And the other thing that it tells us is that no normal force will act on the car because the car is not going to be touching the hill, so the hill can't do any force to it. So using that, we can write down the equation F net equals ma. And we know this is going to be centripetal acceleration because the car is going to be moving in a circle of sorts, so it's centripetal acceleration. And because there's no normal force, the only force on the car is going to be the force of gravity. So, mg equals m, and AC is just v squared over r. And as we've discussed, the radius of the car's motion is going to be 50 meters, because it's just going to graze above the top of the hill. So we can cancel out m, and we can put in the numbers 9.8 equals v squared, which is our variable, over 50. And we can solve for the speed and get that it is equal to 22.1 meters divided by seconds. So if the car goes at 22.1 meters divided by seconds, it's just going to jump over the hill and graze the top of it. Great. Well, that's the first part. Now let's move on to the second part, which asks, what normal force acts on the car at the bottom of the hill if it moves at 10 meters per second? So, first let's see, if the car moves at the bottom of the hill, which force is going to be greater? The normal force, which pushes it upwards, or the force of gravity, which pushes it downwards? I'll give you a couple seconds to think. Okay, so if you imagine the car 0.1 seconds after it's at the bottom of the hill, it's going to be slightly above where it was, which means that it's going to be accelerating upwards, which means that the normal force which pushes it upwards is going to be greater than the force of gravity. So we can use that when writing our equation F net equals mac, and because the normal force is going to be greater than the force of gravity, we know that it's going to be normal force minus the force of gravity equals mac. And we're given the velocity, so we have all of our variables, so we can just write in normal force minus 2,000 times 9.8 equals 2,000 times v squared over r, and v is 10, so 10 squared over r is 50. And we can solve for the normal force, and we get that it's equal to 23,600 newtons. And the car is going to be at the bottom of the hill, so it's going to be doing force upwards. So the direction is upwards. Okay, well that's it. It's pretty simple, and I hope this made sense. And thank you for watching the video.